continuing series on computational fluid dynamics, or CFD. By now you should have built up quite an enthusiasm for CFD, so today we're going to look at some different uses and how it can quite literally shape your world. So join me as we enter the world of science made more simpler. We'll be looking at why we use CFD, how it can be validated in experiments, and the effects of turbulence. But first, who uses CFD?
CFD is used in a range of sciences. It's used in chemistry, engineering, and also in biology. In fact, any area where liquids or gases are being observed can benefit from using CFD as a tool. This makes CFD very versatile and definitely not an overused scientific fad. Before we look more closely at CFD, we need to assess the hazards and risks involved. The words risk and hazard are very often used as if interchangeable. This is wrong, and I will now explain at great length why this is the case. Hazards are the way in which an object or objects cause risk to a person or persons by presenting them with a hazard, whereas risk is the probability of a hazard or hazards causing risk to the person or persons. Hazard and risk, when combined, result in danger. Therefore, both risk and hazard are required to cause danger, although hazard alone can cause danger when risk is applied. Things start to get complicated when we introduce the term exposure. Exposure to a hazard affects the risk of the hazard to cause danger. Remember, a dangerous hazard is always a risky hazard, and vice versa. CFD is free from both hazard and risk. Turbulence. The fluid dynamicist's worst nightmare. So far we've been using CFD to model how fluids behave in ideal conditions. In these perfect systems, particles of fluid will stay within a fixed path. This is known as laminar flow. In most real flows, imperfections in the fluid or in the surroundings cause turbulence. Turbulence consists of random eddies within the fluid. These eddies vary in scale from large eddies to tiny Kolmogorov eddies. The interaction of these turbulent scales is well visualized in this classic sketch by Leonardo da Vinci Code. Accounting for these seemingly random fluctuations is a key part to modern CFD. Modelling fluids at a Kolmogorov scale, while possible, takes huge amounts of computing power. So for practical modelling, we need to be able to estimate the effects of turbulence. Examples of these models include the kappa epsilon model, which uses the kinetic energy of turbulence to work out its effects on fluid. More accurate, but also more complex, is the large eddy simulation, or LES model. The large eddy simulation assumes all scales of turbulence are self-similar, and so, by simulating the large eddies, we can discover what is happening at the smaller scale.
So far we've looked at CFD in theory. Now it's time to put that theory into practice with our first of our real models. Today we're going to be looking at the airflow round a spider. In this experiment we'll be putting our arachnid friend in a wind tunnel created by the use of this household hair dryer. As with any experiment, we'll take the necessary precautions of safety glasses, and because we are handling animals, safety gloves. Well, that's enough science-based fun for now. Remember to join us next time to see what happens when fluids attack. Goodbye for now.